Hello everyone, I am Muhammad Mujahidin Islam and two of my friends MD Rakib and MD Alamgir are presenting Chapter 3 Building the Front-End Layer from Web Scalability for Startup Engineers written by Estmot. Today's web apps are mainly built using three architectural styles. First, traditional multiple applications (MPA). Each click or link reloads the entire web page from the server. This is the oldest model, simple, reliable, and still scalable in many cases. Single page applications (SPA). Here, most of the business logics run in the browser using JavaScript. Only data is exchanged asynchronously with the server using AJAX calls. Hybrid applications, the most common model today, combines full page reloads for some actions and partial updates for others, offers the richness of SPS and the SEO friendliness of traditional MPAs. At the core of scalability lies one principle: manage state carefully. A stateless service does not hold data about the client. Whenever client state is needed, it is retrieved from an external service. In contrast, a stateful service stores some information locally, like session data, temporary files, or logs, making instances unique and harder to scale. Let's look at figure 3.1, which shows a stateful web server setup. Server A holds user A's session data and uploaded images locally. Server B holds user B's data and server C holds user C's. If one server fails, its user loses access to their data because other servers can't reach it. That's the essence of a stateful system, local dependence. Now figure 3.2 shows the stateless alternative. Here server A, B, C no longer store user data locally. Instead, all session data and uploaded files are kept in shared storage systems accessible to every server. Each request can go to any server, making them truly interchangeable. This setup is foundation of scalability, identical independent nodes that fetch shared state externally. The HTTP protocol is inherently stateless. Each request is independent. However, web applications often need to identify users across multiple requests. To achieve this, they introduce the concept of an HTTP session, usually implemented with cookies. Then a user first visits a site, the server assigns a session ID and returns it via a cookie. Subsequent requests include this cookie so the server can recognize the same user session. Figure 3.3 illustrates the process. The client sends an initial request. It has no cookies yet. The server creates a new session, saves data for that session ID in storage, and responds with a set cookie header containing the session ID. Every future request includes that cookie, letting the server retrieve the correct session data from storage. There are three common ways to handle session storage. Session data stored in cookies. In this approach, the server serializes session data, encrypts it, and sends it back to the client as a cookie. When the client makes the next request, the same data is sent back to the server. Figure 3.4 shows this cycle. The browser always includes the session data cookie in each request, and the server updates it as needed. Session data is stored in distributed data store. Here, the server only stores the session ID in the cookie. Actual session data lives in a fast external store such as Redis, Memcached. Figure 3.5 shows this process clearly. The client and server exchange a lightweight session ID, which session data is fetched and saved externally. This preserves statelessness while avoiding large cookies. Sticky sessions via load balancer. The third option pushes the state problem to the load balancer. The balancer adds its own cookie, mapping each user to a specific server. Then it ensures all future requests from that user go to the same machine. Figure 3.6 depicts this mapping. User A's request always reach server A, user B's request always reach server B. While this seems convenient, but sticky sessions break statelessness, limit scaling, and cause issues if server are restarted. Users can lose these sessions. It's better to store all session data externally and keep front-end server runnable. Managing files. The second major type of state in front-end servers involve file storage. Web applications often deal with user uploaded content like images or videos and system generated files like invoice or reports. Files can be public, accessible to everyone, or private, restricted to certain users. Public file storage and delivery via serial. In figure 3.7, the user uploads file to the web server, which pushes them to shared public storage like S3, SCDN, caches and serves these files globally. When users request public content, they usually get it directly from the CDN, reducing the load or origin servers and improving scalability. Private file storage. and delivery. For private files shown in figure 3.8, the process changes. User requests first go through the web application which authenticates the user. If permission is granted, the application fetches the file from private shared storage and streams it to the client. Thus, file remains secure and servers remain stateless because files live externally. Managing other types of state. Even after handling sessions and files, other hidden forms of state can prevent scalability, such as local caches, in-memory application data, and resource logs used for synchronization. In figure 3.9, each server's local cache has a different version of the same item, for instance, different prices for same auction product. This creates dangerous inconsistencies in systems like real-time bidding platform. The solution is to use a shared distributed cache so all servers reference the same object. For less sensitive data like block, follower counts, local caching is fine since minor inconsistencies aren't critical. Now let's examine resource logs, another subtle source of state. Logs are used to prevent race conditions when multiple servers modify the same resource. Figure 3.1 shows a single server setup while the server holds local logs on eBay auction. This works fine on one machine. Only one process can update an auction at a time. However, figure 3.11 shows what happens when the application is cloned. Each server now maintains its local logs, unaware of others. Two different servers could update the same auction simultaneously, creating inconsistent data. This design breaks as soon as we scale horizontally. We can move log management to a shared distributed logging service. In figure 3.12, both server A and B communicate with a shared log service. The log service enforces mutual exclusion globally, allowing servers to remain stateless and scalable.
First of all, take my salam. Assalamu alaikum. I want to say about component of the scalable front end. We can see the figure is detailed front end infrastructure. Here we can see this is client, then this is DNS, and this is CDN. Then we can see this is load balancer, then the request is distributed, and then this is back end layers of our system. Then we can see this is DNS. Here this is clients, then this is DNS lookup, HTTP request, server. Then we can see load balancer. Here benefits to using a load balancer. This is benefits of load balancer. Then this is load balancer, DNS round robin based uh, load balancing. We can see this is client, this is web services, this is round robin DNS. Then we can see this is development with a load balancer. This is client, this is IP, then this is web services, and a regular DNS. This is we can see. Then this is a load balancer figure. The figure is internal load balancer. This is HTTP request, then distributes request, front end web services, then web services.